I want you to imagine, just for a second, like the ultimate predictable universe.
Right, the classic clockwork reality.
Exactly. The kind where if you had a supercomputer powerful enough to know the exact position and momentum of every single particle right now, you could theoretically just hit fast forward.
And calculate the rest of eternity.
Yeah. And that absolute rigorous predictability, I mean, that's been the holy grail of classical physics for centuries. And for a very long time, the poster child for that deterministic worldview was Albert Einstein.
Oh, absolutely.
We all know his famous critique of quantum mechanics, right? God doesn't play dice with the universe. He vehemently opposed the idea of a random chance-based reality where things just happen probabilistically.
He really hated it.
He did. So he built general relativity, his masterpiece theory of gravity, to be this ultimate smooth clockwork machine. But, and here is the bombshell we are unpacking in today's deep dive, technically speaking, it is completely false that general relativity is inherently deterministic.
It's actually one of the most pervasive misconceptions in modern science. And, you know, this isn't just some abstract mathematical technicality isolated to a chalkboard somewhere.
Right.
We were looking at a severe, fundamental failure of determinism embedded directly within Einstein's own theory.
Wow.
Yeah. There are perfectly valid, smooth regions of space-time where knowing absolutely everything about the present state of the universe fundamentally does not tell you the future.
That is just wild to me. Predictability breaks down entirely within the very equations he used to try and banish unpredictability.
Exactly.
Okay, so let's unpack this. Our mission today is to figure out how and why that happens. Because, I mean, if the fundamental theory of gravity isn't predictable, does that mean apples could suddenly fall up? Or are we talking about something far more mind-bending?
We're talking about something way deeper. It's not about an apple falling up. We were looking at the timeline of the apple itself ceasing to have a logically necessary next step.
Oh, wow. Okay.
But to really grasp how that predictability collapses, we have to discard those elementary school analogies of what general relativity actually is.
You mean like the heavy bowling ball sitting on a rubber trampoline?
Yeah, that exact one.
Right.
Making a dip that smaller marbles roll into. It relies on everyday Newtonian gravity pulling the ball down to explain Einsteinian gravity.
Oh, I guess it is a circular visualization, right? It kind of obscures the actual mechanics.
It really does. General relativity isn't just a single equation about a rubber sheet. It's an interlocking five-fold theoretical package.
Okay, lay on me.
First, you have theoretical constraints, like the equivalence principle, that dictates that local effects of gravity are indistinguishable from acceleration.
Like being in an elevator accelerating upwards in space feels like gravity.
Spot on. Then you have the mathematical scaffolding, which is pseudo-Riemannian geometry, on a four-dimensional manifold.
Which is quite a mouthful.
It is, yeah. But basically, this is where we define a coordinate system where time is treated as a geometric dimension, intertwined with space, but with a unique metric signature that, keeps time distinct from the spatial dimensions.
Right, time isn't just another direction you can walk in.
Exactly. Building on that scaffolding, we get the third element, Einstein's field equations. These are highly complex, nonlinear partial differential equations.
They're really scary math.
Yeah, the scary stuff. Fourth is the geodesic equation, which dictates how matter and light travel along the straightest possible paths, the geodesics within that warped geometry.
Okay.
And fifth is the core physical interpretation. The curvature of space-time doesn't just cause gravity. The curvature is gravity.
Right. I've always heard John Archibald Wheeler's famous summary of this. He said, space-time tells matter how to move, matter tells space-time how to curve.
It's a great quote, very poetic.
It is, but doesn't it make the universe sound like it operates in neat, alternating ticks of a clock? Like, first matter moves, then space-time recalculates and warps, then matter moves again, kind of like falling dominoes or a turn-based video game.
Right, and that's exactly why the quote is slightly misleading. It implies a clean, step-by-step causation that simply does not exist in the math.
It doesn't.
No, these equations are dynamically coupled. Everything is happening all at once. It's continuously defining and being defined by everything else simultaneously. Because it's a system of nonlinear equations, the gravity produced by the energy of the gravitational field itself creates more gravity. There is no external ticking clock stepping the universe forward frame by frame.
Wait, if everything is dynamically coupled like a tangled ball of yarn rather than falling dominoes, how can physicists even formulate a concept of before and after to predict anything?
That is the million-dollar question. If there's no universal ticking clock, we need a highly rigorous definition of determinism to even ask the question.
Right.
In physics, a theory is deterministic only if the complete state of a system at any given time uniquely specifies all future states.
And I imagine the heavy lifting there is done by complete state and uniquely specifies.
You nailed it. It means the differential equations must yield one and only one mathematically possible continuation. Physicists separate this into two distinct criteria: local determinism and global determinism.
Okay, let's break those down. What's local determinism?
Local determinism deals with a small, isolated patch of spacetime, just an open set. If you specify the initial data within that restricted local bubble, Einstein's equations beautifully and uniquely dictate what happens in the immediate localized future of that region.
So general relativity actually passes the local determinism test.
It does, without any issues.
So just so you listening can picture this, local determinism is like dropping a pebble into a pond. If you know the exact mass of the pebble, the density of the water, and the impact velocity, fluid dynamics will let you predict the exact height and speed of the first few ripples radiating outward within a 1-meter radius.
That's a perfect analogy.
You don't need to know what's happening on the other side of the lake to predict your local ripple. But global determinism has to be an entirely different beast, right?
Oh, it is. Global determinism requires you to specify the initial data across the entire universe at one single universal moment.
Wow.
And if you do that, the theory must uniquely determine the entire future of that universe, everywhere, forever.
Which immediately presents a massive problem for relativity, doesn't it? I mean, relativity explicitly destroys the concept of a universal now.
Exactly.
Different observers moving at different speeds will completely disagree on two events happening at the same time. So how do we even establish a starting line? How do you take a snapshot of the entire universe at one moment if the universe refuses to agree on what a moment is?
Well, taking that universal snapshot requires the space-time geometry to meet a very specific, stringent mathematical condition.
Okay.
You need to be able to slice through the four-dimensional block of space-time to create what is known as a Cauchy surface.
A Cauchy surface. So that's effectively a three-dimensional, space-like cross-section of our 4D universe.
Yes, but it comes with a strict geometric rule. Every single inextendable causal curve, meaning the entire past-to-future timeline of every particle, and the trajectory of every ray of light must intersect that three-dimensional surface exactly once.
That exactly once rule sounds like the golden rule here.
It is the linchpin. If a particle's timeline never intersects the slice, you have missing data in your snapshot. Something exists in the universe that you failed to capture.
Right.
And if a timeline loops back and intersects the slice twice, you have conflicting data, a single particle occupying two different states at your starting line. A valid Cauchy surface guarantees a pristine, comprehensive initial state.
And if a space-time allows for a Cauchy surface to exist, it earns a special classification, right? It is globally hyperbolic.
Say that 3 times fast. But yes, when a space-time is globally hyperbolic, the underlying differential equations behave perfectly. A foundational mathematical theorem guarantees that your initial data on the Cauchy surface will uniquely determine the maximal globally hyperbolic development.
Okay, let's translate maximal globally hyperbolic development for you listening. Think of the universe as a giant loom weaving a tapestry.
I like this.
The Cauchy surface is your initial row of thread loaded with a specific pattern of colors. The maximal globally hyperbolic development is simply the largest possible piece of fabric the loom can automatically weave based entirely on that starting thread, without the machine jamming or introducing new, uncaused patterns.
Right.
If your universe is globally hyperbolic, the loom runs forever and global determinism is saved. Every event in the future is locked in. So what happens if the track itself is warped beyond recognition? Like, what if the loom jams?
Well, the structural flaw in this idealized picture is that Einstein's field equations do not mandate that the track must be smooth. There are many valid, rigorously derived solutions to general relativity, where the space-time geometry is so radically warped that a Cauchy surface is mathematically impossible to construct.
Wait, impossible.
Yes, the track warps, tears, or folds back on itself, totally destroying the global finish line.
So we are talking about solutions that technically satisfy the math, but completely break our intuition of reality?
Very much so. Things like a charged black hole or a rotating black hole, anti-de Sitter space, where the geometry creates a boundary condition where a particle's timeline can simply end in finite time.
Just end.
Yeah, or where information can infinitely bounce off the edges of the universe. And most famously, we have Gödel universes.
Right, Kurt Gödel. He derived a perfectly valid solution to Einstein's equations describing a universe that is fundamentally rotating, didn't he?
He did. And this cosmic rotation generates extreme frame dragging. It twists the fabric of space-time so severely that the local light cones, the absolute boundaries of cause and effect for any event, begin to tip over.
Tipping over light cones.
Exactly. And if the universe rotates enough, these light cones tip entirely onto their sides, creating closed, time-like curves.
Okay, a closed time-like curve. That is just the mathematical term for a time loop, right? It means a perfectly ordinary path through space-time eventually circles back to its own past. So if you have a Gödel universe, the very concept of a universal snapshot is obliterated.
Completely obliterated. Because if your timeline intersects your own past, then your future state is actively constraining your initial state.
Which means local determinism is shattered too.
Exactly. Your local bubble is no longer isolated. It is being invaded by its own future.
That is just, it breaks the brain a little bit.
Yeah.
But from the source material, it seems like when confronted with these solutions, a huge portion of the physics community historically just labels them as pathological.
Yeah, they do. It's a really convenient academic dismissal. They use it to suggest the solution is unphysical or just a mere mathematical artifact.
Like it doesn't really count, right?
They lean heavily on ideas like Roger Penrose's cosmic censorship conjecture.
Which is just a conjecture, right? Not proven.
Exactly. It's unproven. It essentially hopes that nature will politely hide these unpredictable anomalies behind event horizons, sequestering them from the rest of the observable universe.
Okay, but isn't calling a mathematically sound solution pathological just a fancy way of sweeping dust under the rug because you don't like the answer?
A lot of physicists would agree with you there.
Let's look at the history of physics, right? Regular, non-rotating black holes were once considered pathological. The Big Bang singularity was considered pathological.
Oh, absolutely. Einstein himself initially rejected the idea of an expanding universe. He introduced the cosmological constant specifically to stop it.
Right. And today, quantum field theory routinely demonstrates violations of classical energy conditions. Dark energy violates the strong energy condition. We have no principled fundamental law in general relativity that prevents these non-hyperbolic, non-deterministic geometries from existing.
We don't. And if we accept the validity of these solutions, it forces us to confront what's called the Cauchy horizon.
The Cauchy horizon. So if the Cauchy surface is the foundational data you start with, the horizon is the absolute boundary where the predictive power of that data terminates.
Yes. When the differential equations of general relativity hit a Cauchy horizon, such as the inner horizon of a rotating black hole, they don't simply produce a zero or give you an error code.
What do they do?
They produce an infinite number of inequivalent, mathematically valid extensions.
So the math doesn't crash, it hallucinates.
Oh, that's a great way to put it. Beyond the Cauchy horizon, the universe reaches a point where it essentially says, I have no logically necessary next step. Pick from an infinite array of continuations.
Wow.
New information literally begins to leak into the universe from nowhere, entirely without a preceding cause.
Okay, and this has to be a fundamentally different species of indeterminism than what we encounter in quantum mechanics, right?
Completely different. Quantum uncertainty is entirely domesticated. We have Schrödinger's cat sitting in a superposition of states, and we cannot predict the exact outcome of a single observation. However, the evolution of the quantum state itself is strictly deterministic via the Schrödinger equation.
Right.
And the observable outcomes are governed by strict probability distributions.
Like the Born rule. The Born rule gives us predictable odds. We might not know if a specific radioactive atom will decay in the next 5 minutes, but we know with absolute mathematical precision that exactly 50% of a large sample will decay in a specific half-life.
Exactly.
So quantum mechanics is like a highly trained dog playing a game of chance. The dog might roll a die, and you don't know the outcome, but you know it's a six-sided die. You know the boundaries of the randomness.
Yes, whereas general relativity's indeterminism is feral. There are no probability distributions beyond the Cauchy horizon.
Yeah.
There is no mathematical rule assigning a 20% chance to one reality and an 80% chance to another.
Just pure ambiguity.
Pure, unmeasured, unconstrained ambiguity. The analogy of the Torontonian raccoon perfectly captures this. There are no rules, no boundaries, and absolutely no remorse.
I love that analogy. Here's where it gets really interesting for you listening. Think about that feral raccoon. It breaks into your backyard at 2 a.m., knocks over the garbage can, and eats the dice entirely.
Exactly.
You are no longer playing a game of chance with known odds. You are dealing with pure, uncaused, chaotic possibility. And this feral nature of gravity is so deeply unsettling that you'd think the unified theories we are working on, the ones trying to marry quantum mechanics and gravity, would be designed specifically to tame the raccoon.
You would really expect quantum gravity to resolve this, but the
Yeah.
ironies of theoretical physics are profound here.
How so?
Well, most major approaches to quantum gravity, whether that's canonical quantum gravity, loop quantum gravity, or various frameworks within string theory, they rely on formulations that mathematically require a Cauchy surface just to get off the ground.
Wait, really? They just require it?
Yeah, they demand structures like unitarity and S-matrix formulations.
Okay, let's break those down. Unitarity is the principle that the sum of all probabilities in a quantum system must always equal exactly 1, right? Meaning information is never lost over time.
Correct.
And an S-matrix, or scattering matrix, is a mathematical tool that maps the state of a system in the infinite past to its state in the infinite future. Both of these concepts fundamentally require a stable background time parameter. They require you to be able to define the past and the future globally.
Yes, so by mandating unitarity or relying on an S-matrix, physicists are effectively baking global hyperbolicity into the premise of the theory.
Which is just a massive exercise in circular logic.
It really is. You are demanding a space-time structure that guarantees determinism as a prerequisite for building the theory you will then use to prove the universe is deterministic.
So they're trying to put a leash on the raccoon by closing their eyes and mathematically defining it as a golden retriever from the start.
Basically, yes.
But this kind of circular patch isn't unprecedented, is it? Look at classical Newtonian physics. We always thought Newton's laws were perfectly deterministic.
Right.
But there's that thought experiment called Norton's dome. Have you heard of this?
Oh, yeah. John Norton.
Yeah. So imagine a perfectly symmetrical dome with a ball sitting exactly at the top. Newton's laws say the ball will sit there forever because all forces are perfectly balanced.
Right, classical equilibrium.
But the math actually allows for a second entirely valid solution. At some completely arbitrary random moment in time, the ball just starts sliding down the dome with no preceding cause or force pushing it.
It's mathematically valid. And to prevent that spontaneous movement, classical physicists introduced a mathematical constraint called Lipschitz continuity.
Right.
This constraint strictly limits how fast the rate of change in a system can itself change. It effectively outlaws the infinite derivatives that allow the ball to spontaneously move.
But Lipschitz continuity isn't a physical law. It's a mathematical band-aid. It's an assumption injected into the math specifically to preserve determinism. We assumed Lipschitz continuity for Newton, and now we're assuming global hyperbolicity for Einstein.
Exactly. The definitive takeaway here about general relativity is that it is a framework containing both deterministic and non-deterministic solutions. The theory itself is completely agnostic about predictability. Determinism is not a fundamental property of the universe's governing equations. It is just a contingent property of specific, smooth geometric arrangements.
Which completely dismantles the clockwork universe. I mean, predictability is not a universal law. It is a localized luxury.
It's a luxury we happen to enjoy.
If you happen to live in a smooth, globally hyperbolic region of space-time, the tapestry weaves predictably. But the equations explicitly allow for regions where the loom breaks down, leaving you with the feral raccoon of infinite, uncaused possibilities. Einstein built his theory specifically to avoid the domesticated dice rolling of quantum mechanics, and in doing so, he mathematically proved the existence of an absolute feral chaos.
He really did.
Yeah.
And it forces us to confront how much of our reality is built on local assumptions.
Yeah.
Here's a final provocative thought for everyone to mull over. We know for an empirical fact that supermassive rotating black holes and charged black holes exist in our universe right now.
We've literally taken pictures of them.
Exactly. They are structurally real, which means if determinism is merely a local luxury tied to space-time geometry, the boundaries where predictability terminates those Cauchy horizons, they are physically out there in the cosmos right now.
And that leads to a deeply profound implication, something far beyond just black hole mechanics. Think about the simulation hypothesis.
Right, the idea that our universe is a computer simulation.
Yeah. A fundamental requirement of any computable simulation is an underlying algorithm. State A must mathematically process into state B. A computer inherently requires strict, algorithmic determinism to render the next frame of reality.
But if the universe contains regions governed by feral indeterminism regions where the differential equations yield infinite, non-computable, inequivalent continuations without probability weights, an algorithmic computer cannot render it.
It would crash.
The math cannot be processed sequentially.
So, if the feral raccoon exists, our universe fundamentally cannot be a simulation. A computer requires rules, and beyond a Kachi horizon, the fabric of reality itself simply hasn't decided what happens next. The math is sitting there, utterly blank, uncaused, and waiting.
It hasn't been written yet.
So for everyone listening, the next time you look up at the night sky, realize that we don't live in a clockwork machine, and we don't live in a simulation. God might not play dice, but sometimes God doesn't even show up to the table.